Okay, so I'm going to tell you about some new work that was done in the last couple of months and isn't yet published, and also some old work that was done 25 years ago by various people in many beautiful papers. So what I'm going to tell you about is Berry's phase. So can I just ask who here knows about Berry's phase? Okay, some good set. So I think the plan is that I'm going to spend the first half of the talk telling the rest of you what Berry's phase is. So the story is here that I started reading about Berry's phase maybe a year or two ago, and I just got completely smitten by it. I think it's gorgeous, quite frankly. You know, one of the reasons I'm so enamored by string theory is because there's all this beautiful geometry which fits in so nicely with quantum effects in quantum field theory. So things like D-branes, or the Seiberg-Witten solution, or Calabi-Yau manifolds, and all the things we really love. I have to say, Berry's phase has all of these qualities. It really belongs on this list with the other concepts. But it has one very important difference, which is that it actually exists in the real world, you know, on experiments that you can do on tabletops. It's completely lovely. So actually, I have a cute story about this. I was a postdoc at MIT a few years ago, and Frank Wilczek is there. And Frank is, well, you know, he's very supportive of string theorists, but at the same time, he has kind of a healthy skepticism, I think is the right way to say it, about string theory. So Frank once told me that this is the way he views string theorists. He says that a string theorist is like a guy sitting in a bar and dreaming of this imaginary universe filled with beautiful women, and never once looking around him to see all the beautiful women in the bar that are sort of clamoring around him, waiting to buy him a drink. So when Frank first told me this, I guess I was sort of impressed. I thought that he knows some really, really cool bars that I hadn't been to yet. But when I started reading about Berry's phase, and I think it really rammed the point home. So if people are interested, there's a book by Frank Wilczek and also by Al Shapir called something like Geometric Phases in Physics, or something like this. And it's just a collection of reprints from the 1980s, which was sort of the heyday of Berry's phase. And every single paper in there is lovely, even the ones by experimenters. Really, really nice. In fact, if you really want an example of beautiful mathematics applied to everyday situations, you should check out in that book Frank Wilczek's theory of falling cats. Okay, so you have an SO3 gauge connection over the space of the shape of all cats, and you have to integrate the Wilson line of this gauge connection to understand how the cat turns and if it's going to fall on its feet or its head. So it's really nice. Okay, so having tried to put some spin and convince you that Berry's phase is worth learning, I'm going to now tell you about Berry's phase and then tell you how you can understand Berry's phase in the context of ADS CFT. So there's a few different ways you could view this. You could either see this as a new example of using ADS CFT to compute exact results in strongly coupled quantum systems. So in this case, it's just going to be quantum mechanics, not field theory. But the idea is that hopefully we can push this and use this to understand the quantum mechanics that might actually be useful in the real world, maybe condensed matter systems. The other way, if you're cynical, you can view this is that I'm taking one of those beautiful women from the bar and running away with her to my little imaginary world where I feel safe. Okay, so let me tell you about Berry's phase. Berry's phase is the following. You have a quantum mechanical system, which is here, and you've got a set of energy levels, and I'm going to assume for the purpose of the next 2 minutes that these energy levels are not degenerate, meaning there's one eigenstate per energy level. Okay, so here's my quantum system. And over here I have my experimental apparatus with dials on. And I can change these dials, and as I change these dials, it's changing the various parameters of the Hamiltonian that describes this quantum system. Okay. So I change the dials, and what happens, the energy levels start to move, obviously, because I'm changing my Hamiltonian. So what I want to do, well, firstly, let me just say I'm going to just normalize things so the ground state always stays at the same energy level, just for convenience. I don't have to. So change the dials, ground state stays the same, but all the other guys start to move. Now, occasionally, as I vary the dials, one of these higher excited levels will come down and become degenerate with the ground state. Okay? It doesn't happen often. It's quite rare. It's quite rare because when you do first-order perturbation theory in quantum mechanics, there's that factor of 1 over em minus en, and it kind of gives a repulsion of the energy eigenvalues. So it turns out that you have to essentially dial 3 parameters to just the right point to get these things to coincide. These degeneracies are codimension 3 in parameter space. Okay, so what I'm going to do is I'm going to dial my my knobs over here, and the energy levels are going to change, but I'm going to dial them so that you don't get degeneracy, so that this one never comes down and hits the ground. Okay. Good. Now, let me prepare my system so I sit in the ground state. I have an eigenvalue of the ground state. And I start to change my dials. Things change. If I change the dial slowly enough, the adiabatic theorem guarantees that I remain in the ground state all the time. Okay? If I dial them quickly, I'll jump between states. If I dial them slowly, I always remain in the ground state, and these upper ones are just varying along. Now, the question I want to ask, the question that Berry answered in generality, is suppose I do a loop in parameter space. So I change my dials, and eventually, after a lot of fiddling, I get back to where I started. Because I changed them very slowly, the state I started with, which was the ground state, remains in the ground state and comes back to itself up to a possible phase. And the question I want to ask is, what's that phase? Okay, now you might think phases of wave functions are not measurable, doesn't matter. It's not true here because what we're really talking about is a phase difference. Okay, I could prepare 2 systems, put them both in the same state, leave one alone, but change the dials on the other, come back round, and then interfere the states. So it's a measurable quantity, and in fact it's a measured quantity, and there's been many experiments now that have measured this phase. Okay, so what is the phase? Well, there's always this dynamical phase. You know, there's always this e to the minus I et, or where e is the energy of the state only. But let's get rid of that. Let's just say the ground state has 0 energy for all values of the parameters. Okay, so now you might think that, well, it's 0 energy, so e to the minus I 0t is 1, so the phase doesn't change. And that's not true. So Berry tells us that there is a phase difference as this wave function moves around. And the phase tells us which path we took in parameter space, how we change the dials. Okay, so what I'm going to do shortly is just tell you how that works. Before I do that, let me just tell you a generalization of Berry's phase due to Wilczek and Z from 1982, and it's Berry's original paper was also 1982, by the way. And it's a non-abelian version of Berry's phase. Okay, so what this system says is suppose I have a quantum system where the ground state has n-fold degeneracy for all values of the parameters. Okay, so there's n possible ground states, and as I vary my dials, there remain n possible ground states all the way along. Okay, so now I have the following question. I start off in one of the ground states, I change my dials, I start to move, I come back to where I started from, I'm still in one of the ground states, but the question is which one? So now rather than just having a phase change, there's a full UN rotation where the initial ground state could have been rotated into any of the other ground states. Okay, so in this case, there's a UN phase, or strictly speaking, a UN holonomy as I vary the parameters. Okay, so let me explain to you how Berry's phase works. So this is the non-abelian Berry's phase. And it's due to Wilczek and Z. Okay, so this blob here is going to be my space of parameters. Okay, so this is the parameter space. And for this part of the talk, I'm going to call my parameters lambda. I'm going to change the notation shortly. Okay, so every single point in this phase corresponds to a particular position of all the dials. Okay. Now, at each point in this space, I'm interested in the space of ground states. I should say it doesn't have to be ground states. I could have asked the same question for any of the energy levels. Ground states is the easiest. In fact, later in the talk, I'm going to consider excited states. Okay, so above every point, there's the space of ground states. So this is the space of ground states. And just for normalization, I'm going to choose, it means some of these tricky dynamical factors go away, that the ground states have energy 0 for all values of the parameters. Okay, so at this point I've got a space of ground states. If I choose another point, I've still got an n-dimensional space of ground states, but in the full Hilbert space, it's rotated slightly. It's rotated because this is a different Hamiltonian, it has different parameters, and as I change the parameters, where the ground state sits in the Hilbert space is going to change. Okay, good, so this is my space of ground states. So now I do the following. At every single point lambda, so for every parameter, I introduce some basis vectors for the space of ground states. So n1, n2, here, n1, n2. No, it's certainly not a tangent space. So this parameter space is the space of all these objects live in very different spaces. This is the space of all possible positions of the dial. Okay, so that's what's over here. Okay, now over here is my box, which is my quantum system, which has a Hilbert space, and this object here is the ground states that live within the Hilbert space of this quantum system. Okay, now I change my dials and the ground state changes in the Hilbert space. So that's what I've tried to show by this tilting. Exactly. Yeah, that's exactly the point. That's really the key point of the Hilbert space. Okay. So for each set of parameters lambda, where lambda is some vector, introduce an arbitrary, and this word arbitrary is really key, set of bases for the space of ground states. Okay, so my space of ground states is n-dimensional for all values of the parameters. The number of parameters is denoted by a vector here, and I've left unspecified, but it can be anything you like. So the A runs from 1 to n, and exactly what the basis vectors do depends on lambda, which again is the statement that the ground states in the full Hilbert space change as you change them. Okay, so what we want to know the evolution of a state psi, and of course it evolves under the time-dependent Schrödinger equation. But the Hamiltonian depends on the parameters lambda, and I'm changing my dials very slowly, so the parameters lambda in turn depend on time. Okay, so this is the time-dependent Schrödinger equation, but what I'm really interested in is the evolution of the ground state of the system. So this is equal to 0, okay, because it's the ground state, and because I've set the energy level of the ground state to be 0. Okay, so what am I going to do? What I'm going to do is so this is the true evolution of the ground state, and it's going to be equal to some unitary matrix, which will depend on time. times this arbitrary basis of vectors that I put for each ground state. Okay? So as I'm moving in time, I move along here, the ground states are going to shift. I've got this arbitrary basis at each point, and I'm simply expanding here the true evolution of the ground state in terms of the basis vectors that I've picked at each point. Notice that here I've actually assumed the adiabatic theorem. Okay, the adiabatic theorem being that if I change my parameters slowly enough, I'm not going to jump from the ground state into another state. So I'm assuming that I remain in the ground state. Okay, so now it's very easy. What I have to do is determine this evolution matrix, which tells me how I expand the way a state evolves in terms of the basis. So all I do is I plug this into here. To get the following rather simple equation. And then what I do is multiply by the inverse of u, but u is a unitary matrix. So I multiply by the inverse of u to put a u dagger here, and then I take the overlap with some other vector nc, but because these are basis vectors, they're orthonormal. So what I get from this is that u dagger ac u dot cb is given by the following. But the time variation of these basis vectors is coming because I'm dialing my parameter. So I can just expand this as following way. And then what I'm going to do is just call this object that sits here a name. And I'm going to put in a factor of I because that makes this a mission connection. Okay, one small subtlety here, the B and the A get swapped around from the A and the B up here. Okay, so this A is a Hermitian UN connection over the space of parameters. Okay, it's UN because it has these indices here, A and B, each of which goes from 1 to n. And the vector here is saying that it's over the space of parameters. Okay, so if you think of like a gauge potential in Yang-Mills theory, it's an A mu and then an A and a B index. The A and the B index are the UN, and the mu index of A mu in Yang-Mills theory is this sort of vector here. Yeah.
Is it dependent on lambda also? Or is it dependent on lambda?
So let me see. Yeah, all the time dependence is coming by varying lambda. So yes, this u depends on lambda. In fact, I'll show now that it only depends on lambda. It doesn't depend on t in a way that I'll make precise. Okay, so we have an expression. What we want to figure out is u, and we have this expression here in terms of what I called a. But if I've defined my basis vectors, so if I really know what my ground states are for all values of the Hamiltonian, and I've defined these basis vectors, then I can certainly take one basis vector, differentiate it with respect to lambda, and then take the inner product with the original basis vector. So this a is something I can calculate. Okay. Okay, but these kind of equations, these matrix equations, U inverse U dot equals equals some object A, are things we know how to solve. Right? I think the first time you come across them is when you think about rotations of rigid bodies in undergraduate mechanics. And so the answer is that U of t is given by the path-ordered exponential. I guess you also see this as Dyson's formula in quantum field theory. Okay, so what you get is U that tells you how this state is evolving. It's given by the Wilson line. I haven't necessarily closed this yet. If I was to do a complete circuit, it would really be the Wilson loop of this connection, this UN connection, over the space of parameters. And this is what I meant when I said that it doesn't actually depend on time. The time drops out here, and it just depends on the path you take in parameter space, not how long you take to get there. You've got to do it slowly to make the adiabatic theorem work, but other than that, it just depends on the path. On path in parameter space. Not the timetable. Okay, so that's rather cute. Have a quantum mechanical system, depends on some parameters, and for every state in that quantum mechanical system, for every energy eigenlevel, avoiding degeneracies, you can define a connection over the space of parameters where the connection is a UN connection, where the n was the degeneracy of the states you were considering. So here I've done it for the ground state, but as I said, I could have done the same thing for any excited states. Okay, so within these very simple quantum mechanical systems, is this rather nice geometry. Let me just show one thing to you, which is that this, I keep calling this a connection. It really is a connection in the sense that we know and love. So, when you have a connection, it has this transformation under gauge transformations that includes this homogeneous part, the derivative part. So what are the gauge transformations here? Well, gauge transformations is to do with the redundancy in our description. And the redundancy here was how I chose these basis vectors in the first place. I chose these completely arbitrarily. I could just as happily have picked a different set of basis vectors at every single point lambda. So suppose we picked different basis vectors. Prime A. Okay, so at every point lambda, I can do a UN rotation, but the choice of UN rotation can itself depend on lambda. Okay, so I can choose not to rotate here, to do some arbitrary rotation here, for example. Okay, if we plug this into the definition of the connection, what we find is that A prime transforms exactly as a connection should do, complete with this inhomogeneous term, this derivative piece. Okay, so this A really is a connection. It has the correct transformation. Okay, so again, this is really the key formula. Oh, I should say, this flip between the B and the A and the B here essentially makes this transformation work out with the overlaps. Things contract in a nice way if you define it this way. Okay, so the key formula is really this. It's the fact that there's a connection defined in the following way. At every point, you take your basis vector, you see how that basis vector changes as you change the parameter, and then you take the overlap with all the other basis vectors. This defines a connection. Okay, so I'm just about to give an example, but are there any questions before I do. Yeah.
Small and dimensional space vector.
Sorry, say that again?
The small
The small n is the dimension of the ground state space, and so that's this vector here denotes an index which runs from 1 to... Oh no, yes, sorry. These indices here run from 1 to n. This vector here runs from 1 to the number of parameters that you have. That's the number of dials you have in your apparatus. No, sorry, I said it all wrong. Let me start again. N is the number of ground states that you have, and the number of dials, let me call it the number of dials, and this vector here is an index which runs from 1 to the number of dials. Okay? Number of dials, number of ground states. In this case, I've said that the ground state is degenerate. Typically, it won't be. And in fact, most systems, not all, but most systems in, say, condensed matter physics, where Berry's phase is relevant, it's actually just a U1 Berry's phase because you don't have the relevant degeneracy. You just have the simple phase. Yeah.
Just because shouldn't there be minus? Because you move it to the other side, right? So you get minus u the n dot, and then you multiply with the other side, so it should be a minus side.
Oh, you're absolutely right. Good. So there's a minus on the first one and the second one, and that minus.
Right.
Okay.
So you have to change your definition.
Okay. So this is true up to minus. Yeah. Yeah. Sorry, I wasn't too careful this morning. Yes, I think you're right. Okay. Any other questions? Yeah. Sorry, I didn't hear. How do we? Oh, absolutely. Right. So typically it will change, and you need typically some special symmetry in order for it not to change. So there could be some global symmetry, there could be supersymmetry, and the Witten index always guarantees n ground state. In condensed matter systems, there's something called Kramer's duality, which is the statement that if you have an odd number of fermions and a time reversal invariant Hamiltonian, all states come in pairs. So there are various ways to build the degeneracy. The example I'm going to give in string theory has exactly a degeneracy, and we'll see where it comes from then. We're assuming the n doesn't change. Yeah, that there's, when these energy levels are varying, you've got to assume that this guy never comes down and hits this guy. I'll give the example, and then maybe it will be clearer, because that will have something which shows up exactly what happens when you get a degeneracy. Are there any other questions? Okay. Good. So let me give you the example. This is the canonical example that Berry first introduced in his original paper. And it's very simple. It's just a spin-half particle in a magnetic field. So an example. And this is an example of an abelian Berry's phase. Where abelian means n equals 1. I only have a single ground state for all values of the parameters. Okay, and the example is a spin-half particle. In a magnetic field. And I'm going to call the magnetic field capital X, which I know is completely ridiculous notation. It should be called capital B, but you'll see shortly why capital B would be much too confusing. So I'm going to call it capital X. Okay. So question? No. Good. So what's the Hamiltonian? Well, the Hamiltonian is simply it's a two-state system. Your Hilbert space is two-dimensional. These are the Pauli matrices. And this X is the magnetic field. This X is the B dot sigma. So what's the energy spectrum of this? Well, the energy spectrum is you have two states, one with eigenvalue plus X, where X is the mod of this vector, and one with eigenvalue minus X. Okay, so this is E. X are the parameters, so X are what I called lambda before. me just stress that. They're the parameters we're going to be varying. And well, maybe I should call that mod x and get rid of this side. That would be better. Okay. So the energy eigenstates are just plus and minus mod x. Okay, so if, for example, x points in the third direction, magnetic field points in the third direction, then the energy eigenstates are just the eigenstates of sigma 3, the third Pauli matrix. However, as you vary x, it's obvious that the energy eigenstate is moving in the Hilbert space. By the time x points in the x1 direction, it's now the eigenstate of the first Pauli matrix. Okay, that's very clear. So what I'm going to do okay, so we'll look at the ground state. Which has eigenvalue minus x. The last time I said I was going to put the ground state to have 0 energy. I could always do that just by adding mod x here. It's not going to change anything at all, so it's not really relevant for what happens. And what we want to do is compute Berry space. Or more precisely, we want to compute Berry's connection, defined in this way. Okay, so this is completely trivial to do, right? What you should do is set x in one direction. You have a particular combination of the Pauli matrices. You figure out the eigenvector of the Pauli matrix. You then see how that eigenvector of the Pauli matrix changes as you vary x, and then you take the overlap with the original guy. Okay, so it's going to be an exercise if you want to do it. Just to see how this works, it's very easy. And what I'm going to do here is tell you the answer. In fact, there is a small subtlety to do with the fact, as you'll see shortly, that you actually need 2 different coordinate patches for the bases. So it's a little tricky. So instead of telling you the Berry's connection, I'm going to tell you what the Berry's curvature is. So the answer, so Berry's curvature is just defined as the field strength of the connection. Okay, so this is the equation for Berry's curvature. This is obviously a very familiar equation, but nothing in this equation is what you think it is. Okay? Usually in this equation, A is the electromagnetic gauge potential and X are the coordinates of space. It's not the case anymore. X, which were the coordinates of space, is now the magnetic field itself. This is why I said it would be very confusing if I called this B. Right? So X is the magnetic field, and A is this connection over the space of parameters, which is a connection over the space of the magnetic field itself. Okay? So familiar, but everything is different from what you're used to. Yes? Oh, good. Sorry. So I goes from 1 to 3. And yeah, sorry, I just introduced that out of the blue, but it's this index here. Yeah. Okay, so you can compute this. Like I said, it's a fairly simple exercise to do. And this is what you find for the connection, or sorry, the curvature. Okay, so what is this object? This should be something that you've seen before. This is what we would usually call a magnetic field. And this is a radial 1 over r squared fall off for a magnetic field with a singularity at the origin. So this is precisely the formula for a Dirac monopole. Okay? So what we have, this is a Dirac magnetic monopole This is why I said there's a small subtlety if you write down the connection, because those of you who know these things, there's a Dirac string when you write down the connection for a U1 Dirac monopole. And you've got to just define things in a way to avoid the Dirac string. So it's easier just to write down this. Good, very good question. Yes is the answer. I'll tell you a bit more shortly. Okay, so what do we have? We have the space of all magnetic fields. So this is R3, space of magnetic fields. Space of magnetic field X. Now, over the space of magnetic fields is a U1 connection, which is precisely the Dirac monopole. As was just pointed out, in the middle of the space, when x is 0, this has a singularity. This reflects the fact that the two states become degenerate here, and the whole discussion was predicated on the fact that one state never came down and hit another. Okay, now what can I do? Let me take a path somewhere a long way away from the singularity. So this is my path in parameter space. This is me changing my magnetic field. The ground state comes back to itself up to this phase, which by Stokes' theorem is simply the flux that this magnetic monopole emits that goes through the surface of this loop. Okay. Okay, there's something quite cute here. You know, the Dirac monopole is called the Dirac monopole because Dirac was the first person to discuss it. Of course, he discussed it really in the context of electromagnetism, where this A was really the A that we know and love in electrodynamics. That was in 1931. In fact, the gauge potential for the Dirac monopole was written down 2 years earlier, including the Dirac string, by Van Vleck in the context of Berry's phase. He was thinking of two atoms moving around and incubating out electrons around it. So he didn't know it was Berry's phase, Berry wasn't born, and he didn't know it was the Dirac monopole, but nonetheless, that's the first place in the literature that the connection for a Dirac monopole appears in this context. Okay, so there's a few points I want to make out, I want to say, just to sort of touch base with string theory a little bit. The fact that there's a singularity that appears here is very familiar in string theory context. We often do situations in string theory where we see singular behavior, and what it's telling us is that in this Wilsonian approach, we've missed an extra light state which comes down. This is true for, say, the conifold singularity or Seiberg-Witten theory. That's exactly what's happening here. We're focusing on this object, but where there's a singularity, we've missed an extra state which is becoming degenerate in energies. The second point is that even if we're a long way away from this singularity, it's really its existence that's dictating the physics. You know, this singularity is emitting out this sort of pseudo-magnetic flux in this abstract space. And if you take a path, it's the flux that goes through that path that's telling you the change of the phase. So you can avoid this singularity as much as you like, but its presence is still felt. That's also something that's rather true in string theory. The singularities in the Seiberg-Witten plane dictate the whole solution for you. It tells you what the physics is everywhere. Okay, good. So that's my summary of Berry's phase, and I'm now going to tell you how it appears in string theory, and then T. So are there any questions? Yeah.
How does the old quantum mechanical idea still work? I mean, I could imagine the ground state is this, and then this, and then this, and I could sum over all of the.
No, and the ground state doesn't have to come back to itself any more than when you re-enter the same room, you have to be wearing the same clothes you wore the day before, right? you change the state, you come back to itself. It can be a different state. It can be a different state just up to a phase, or in the UN case, a completely different state. There's no reason it has to be the same. You might be confused with the argument about quantization of electric charge in a magnetic monopole, where there's single valueness of the wave function, things like this. It's not quite the same story here.
But are you going to discuss how we see this thing? I mean, how do we observe this?
Oh, good. So what you could do, for example, is you take two systems which you prepare in the same state. You then separate them carefully. This guy, you change the magnetic field. You then bring them together. You then interfere them, and then you see this phase. Yes.
So if I do deformation of the path, and I change everything.
Absolutely. What it's really measuring in this particular case is the area of the path on some given two-sphere. Yes. I mean, that's not standard of all various phases, but it's always path dependent and not time dependent. It doesn't depend on how long it takes you to go around the path. Yes.
When you replace quantum mechanics with this quantum space, which is just a space with a particular metric.
Good.
And this formalism, Berry's phase, is literally the connection on the quantum phase space.
Good. That's very ADS-CFT. We should talk later. There was another question here. Yeah, so we don't have electric charge here. Remember, this is just some different gauge connection. It's not really the thing for the electric charge, but the argument still goes through. The argument for the quantization of electric charge essentially boils down to the fact that when you take this loop around and then look at the surface integral here using Stokes' theorem, there's an ambiguity. I can either close the surface this side, or I can close the surface this side, and those two better agree up to a factor of 2 pi. That's how the charge quantization argument goes. So the same holds here, and you do indeed get a quantization of this number here. It's came out as the number 2. This is related to the fact it's a spin half particle that we started with in a magnetic field, and it does indeed satisfy the minimal Dirac quantization condition in that sense. It's not really electric charge though. It's a little. Was there another question here? No? What happened? You good? Okay, good. So Berry's phase in string theory. Okay, so this is work with 2 students in Cambridge, Chris Pedder and Julian Sommer. Okay, and the system I'm going to look at is the system that we already saw yesterday. It's the system involving instantons, so it's the D0 D4 system. Okay, so I have n D4 branes here. I have a single D0 brane. Remember yesterday I used K, I'm just going to pick 1 here. I'm going to have the following coordinates. These are the same notation I used yesterday. Y is parallel to the brane and X is transverse to the brane. So X, remember, is in the vector in R5 because there's 5 dimensions transverse to the brane. Okay, so what I'm going to do is write down the action for the D0 brane. We saw it yesterday. I'm going to ignore the directions in the Y, motion in the Y direction. You see, it's completely translationally invariant in that direction. It's only interesting if you have more than 2 D0 branes and they can separate. If you just move, it just sees the same thing all the time. Okay, so ignoring motion in the Y direction, the dynamics of the D0 is governed by a Lagrangian with 8 supercharges. And this effectively fixes the Lagrangian completely. Okay, so it's okay, so these are the 0, 0 strings. The X just tells you the position of the D0 brane as it moves in this way, and the lambdas are the fermions, which are the superparticles of the X. So usually you don't write down the fermions. You know, the beauty of supersymmetry is you never have to talk about fermions, but here they're kind of important. This 1 over G squared here is in suitable units with L strings and such like, the mass of the D0 brane. Okay, so this is a half m v squared. Okay, these are the 0,4 strings. The 0,4 strings, remember, come with hypermultiplets. So that's 2 complex scalars, and the I index tells you which D4 brane the string is ending on. Again, I need to include the fermions. All these guys are electrically charged under the U1 gauge field. This has charge +1, this has charge -1, these have charge +1. This alpha index here goes from 1 to 4, and is the number of spinors that sit in the hypermultiplet. Okay, there's a couple of extra important terms. There's this term here. This tells you that when you pull the D0 brane out, turning on a string is going to cost energy. There's going to be a mass involved, which is where the mass squared is proportional to x, the distance. So that's what this term says. If you turn on x, move the D0 brane out, you get masses for the hypermultiplet scalars. And now comes the all-important term. This is a mass term for the fermions, but the mass term for the fermions comes with a particular mixing, and I'm going to tell you what this is shortly. And then there's a bunch of other terms. There's some Yukawa terms that involve the lambda, the phi and the phi tildes, and there's some potential terms, and I won't bore you with them. I wrote down the potential terms yesterday. Okay, what are these lambda objects here? Well, x is a vector in R5, and alpha and beta go from 1 to 4, so these should be 5 4x4 matrices. And in fact, they satisfy the Clifford algebra. And so these are simply the gamma matrices in 5-dimensional Euclidean space. Okay. So for those of you who know a bit about supersymmetric theories, the theories with 8 supercharges, which are like n equals 2 in 4 dimensions, the natural place to live is up in 6 dimensions. Okay, that's where 8 supercharged theories live. When you dimensionally reduce from 6 dimensions to quantum mechanics, you sort of pick up a 5 dimension, which leads to an SO5R symmetry. It's the fact that those 5 dimensions you dimensionally reduced on are what give you these gamma matrices that sit there. See, these terms originally were covariant derivative terms, where these were parts of the gauge field for the spin. Okay, good. So this is our Lagrangian, and sorry, say that again. Yeah, so there's still an A0 which is sitting in here. So it is gauged quantum mechanics. Yeah, these are the ones that have charges. And that's actually important, and I'm not sure I'll have time to tell you that stuff. If I do, I will. Okay, so this is the Lagrangian, and the first thing you'll notice is there's not actually many parameters. And what supersymmetry does for you is fix all the terms in the Lagrangian. And what we want to vary to get Berry's phase are parameters. So the only thing we have here is the mass of the D0 brane, but it's not really going to lead to anything interesting. So that's not what I want to vary. What I'm going to do instead is actually what everybody does in condensed matter literature as well, typically when discussing Berry's phase, which is use the Born-Oppenheimer approximation. So let me just explain what that is. Okay, so the Born-Oppenheimer approximation is really Wilsonian effective field theory applied to quantum mechanics. Okay, it's the simplest version of Wilsonian effective field theory. What you do is you say, suppose I have a separation of energy scales. The original context was a bunch of very slow, cumbersome moving nuclei with a lot of very fast electrons whizzing around. In this case, what I can do is treat the nuclei as essentially fixed, because the time scale on which they move is much, much slower than the time scale on which the electrons move. So I treat them as fixed. I treat their positions as parameters. I then figure out what the electrons are doing in that fixed background. I then integrate them out to come up with an effective theory for the nuclei. Okay, so that's the Born-Oppenheimer approximation. It's exactly the same as Wilsonian ideas in quantum field theory, except there's this cute inversion between heavy and light. Right? So in quantum mechanics, you integrate out the light states, you integrate out the electrons that are buzzing around. In field theory, you integrate out the heavy states. Okay, so the common terminology is fast or high frequency. In both cases, you integrate out the high frequency modes. For quantum mechanics, the difference is that the light states and the heavy states actually exist there in front of you. You can touch them. For field theories, typically when you talk about integrating out the heavy fields, you don't actually have those heavy particles in front of you. You've put them in their vacuum state and you're figuring out virtual effects. Okay? So in both cases, you integrate out fast modes. In relativistic field theories, fast modes are heavy fields, essentially because of E equals mc squared. In quantum mechanics, fast modes are light fields. Okay, so there's that nice little switch of terminology. So what are we going to do here? What we're going to do is make the D0 branes heavy. So this means G squared goes towards 0. Okay, so G squared goes towards 0, or G string goes towards 0, means this D0 brane is going to be very heavy, and I'm only going to be interested in the quantum dynamics of the 0-4 strings. Okay, so I'm going to ignore the fact that the x's are dynamical. I'm going to fix them because the D0 brane is moving very slowly. And then the action for the 0-4 strings, which is this, the x's simply appear as a parameter. Okay. Okay, so the 0-4 strings are like the fast electrons. The D0 brane is like the heavy nuclei. It turns out that because of factors of L string and stuff that go into this, the actual requirement is that G squared, which has dimension 3 in quantum mechanics, is much smaller than X cubed. Okay, so now we're going to now we're going to look at the quantum mechanics for the 0-4 strings with X as a parameter which we can vary. Okay, so the cute thing about this Lagrangian is now we've got rid of all the complications. You know, that this was when X is a dynamical field, this is a quartic interaction, and it's sort of complicated to deal with. But when x is the parameter, this is just a quadratic interaction, and the whole thing is completely free. Right? It's just free field theory or free quantum mechanics. So this is the advantage of going to the Born-Oppenheimer approximation. The only small subtlety we have is that there's still an A0 student there, and I'll tell you how to deal with that shortly. Okay, everybody's gone silent. Are there any questions?
In the A0 dynamical, it's just pure gain.
Yeah, but it poses a constraint. It imposes Gauss's law constraint, which you have to deal with. Any other questions? Okay, so let me tell you what you do with this, and let me start just by telling you how you quantize fermions in quantum mechanics, because fermions in quantum mechanics are kind of different from fermions in higher dimensional theories. Essentially, for every fermion you have in quantum mechanics, your Hilbert space splits into two. Okay, that's what fermions do for you. They're essentially the same as writing down your Hamiltonian in terms of matrices. In fact, you can always swap the fermions for matrices. Remember the Hamiltonian I gave you for the example of Berry's phase was in terms of Pauli matrices. So typically when we write down Lagrangians, we never write down a Lagrangian in terms of a matrix. We always just have some C number expression. But you can always place the fermions here for matrices. So let me just explain what's going on with that. So how to quantize fermions. In quantum mechanics. Well, it's fairly easy. We go to the Hamiltonian picture. The first thing we do is figure out the conjugate momenta to the fermions. That, of course, just like in field theory, is psi bar. So we have the following anti-commutation relations from field theory. The difference is now that in the canonical formalism, these of course now don't depend on space-time because we're just dealing with quantum mechanics. So this is just the algebra for creation and annihilation operators. So our Hilbert space this should read, find some vacuum state. This is some state which is annihilated by all the psi's, and the Hilbert space is given just by hitting with the psi betas. And I'm going to leave that Lagrangian on there, so I'll come over here. Okay, so this is the Hilbert space you get from acting with the fermions. Now, of course, you also have the bosonic wave function that you have to deal with. So this zero here could be any function of the bosonic fields. Okay, so let's look at the multiplicity of this Hilbert space. This is 1, this is 4, this is 6, this has 4, this is 1. Okay, they have 6 and 4 because everything is anti-symmetrized, of course, because they're fermions. Okay, so like I said, we have to worry about the bosons. The bosons have a fairly trivial Hamiltonian. There's just some kinetic terms. This was a Lagrangian, that should really be minus. Plus these mass terms, so they're just free harmonic oscillators. There's 4 of them because these are 2 complex objects. But we should look at the action of the fermionic Hamiltonian. And the fermionic part of the Hamiltonian is simply this. Okay. The Lagrangian is already the form P q dot, so you just take off that on the left just with this. So what we want to know is how this fermionic Hamiltonian acts on each of these states and what the eigenvalues are in each sector. So notice that what this is doing is it's killing one of the fermions, rotating you slightly in a way that depends on x with these gamma matrices, and then creating a slightly different fermion in a different direction. Okay? So in each of these sectors we want to know how this acts. So the energy eigenvalues of HF, well, the first one, the psi just comes and kills it, so that's 0. Okay. The next one, it kills it, it rotates it, and then it puts it back again. So you can convince yourself fairly easily, just by checking, that the eigenvalues here, there's 2 eigenvalues minus x and 2 eigenvalues plus x, depending on the distance. Notice this is kind of reminiscent of the example I gave, right? The example I gave was x times Pauli matrices. Now I've got x, which is a 5-dimensional vector, times 5-dimensional gamma matrices. Okay, I guess the first one you could think of as a 3-dimensional vector times 3-dimensional gamma matrices. So it's sort of the 5-dimensional version of what I had before. And these psi's here, like I said, are just changing the Hamiltonian from something which is a C number to a matrix. Okay, so moving on, here we have a minus 2x and a plus 2x, and then there's a bunch of zeros. Here we have the same as this, and the whole thing is invariant under some charge conjugation symmetry. And here we have 0 again. Okay, so let's try and look at what states are interesting for us, and the first thing we should look at is the ground state. So the ground state, and the ground state should be the fermion with the lowest eigenvalue. So that sits in this guy here. The lowest eigenvalue we can get is minus 2x. Now we know in supersymmetric systems that the ground state always has 0 energy. So how is that fitting with this minus 2x? Well, the extra bit comes from the bosonic part of the Hamiltonian. Okay, so the ground state as E equals, so it sits somewhere, some combination of these 6 states, and which combination you pick depends on what x is, of course. So the energy of the ground state has a fermionic contribution and a bosonic contribution. Apart from the fermionic contribution is minus 2x. That's just this fermionic Hamiltonian acting on this. But now we have 4 bosons, or 2 complex bosons, and each of them has a mass x. So we should add 4 times a half h bar omega, where h bar omega is x. Okay, so we add from the bosonic part plus a 4 times a half x, and this is 0 as you expect. Okay, so yeah, so there's a unique ground state. I should just say this is in the Born-Oppenheimer approximation where everything is trivial. If you go back to this original theory with these dynamical and these Yukawa potential terms, the conjecture that this theory has a unique supersymmetric ground state is very important for the whole understanding of the zero branes Kaluza-Klein modes coming down from M theory. So it's one of the conjectures that was about concrete quantum mechanical models that was made in the mid-90s when M theory was first discovered. And it's unbelievably hard to write down a wave function for this complicated quantum mechanical system. So there's a nice paper by Sethi and Stern which essentially shows just how hard it is. And they don't solve the problem, but they at least write down all the differential equations you have to satisfy and show remarkable simplifications, but it's still really hard. I have a feeling I saw a paper by mathematicians who claimed to prove a unique solution to these differential equations. So I think it's been proven, at least for the case of 1D4 brane, but not for many. Okay, that was a bit of a tangent. Let's now look at the excited states. They're going to be the things that are actually interesting. So the first excited states So we have two states in this sector and another two states. So each of these sectors has 4 states, and in each sector there's 2 of them that have fermionic eigenvalue minus x, which means when we put the bosons in their ground state, we're still going to add a plus 4 times a half x. So these are going to have the excited states, the lowest excited state, whose mass is x, whose energy is x. Okay, so these are going to have E equals EF plus EB, which is going to be a minus x from the fermionic part plus 4 times a half x from the ground state energies of the bosons, and this is going to be plus x. Okay, so what do these states correspond to in the string theory picture? Well, here's the D4 branes, here's the D0 brane, and a state with energy plus x. Simply to put a real honest-to-goodness string sitting there, not a virtual string, but an on-shell string stretched between here and here. Stretches a distance x, and when you take into account the L strings, which are already embedded in this notation, the energy of that object is going to be x. Okay? Turns out there's 4 such objects, 4 such strings with slightly different quantum numbers to do with which fermions you turn on, 2 from this sector and 2 from this sector. Okay. Good. So now I'm going to ask the following question. Let me get rid of this now. Yeah. Sorry, who asked the question? No, when the bosonic Hamiltonian, which I unfortunately just rubbed off, was simply that of a harmonic oscillator. It was kinetic terms for 2 complex scalars plus mass terms for 2 complex scalars where the mass squared was x squared. So the ground state of the bosons is the usual Gaussian wave packet, which has energy a half times x.
So if I take the ground state of the fermions, the excited state of the bosons, is this lower line then?
No, that. Oh, I'm sorry. No, it's not. You might think that you could get to the same, but you can't for a reason I'll explain shortly. It's to do with Gauss's law. The states I've even written here don't actually exist in the system because they carry a charge +1. See, the fermions are charged, the psi's. So these states are all charged, and to make them consistent with Gauss's law, you have to actually add a charged state to the bosonic sector as well, which lifts the energy. I'll come to it. It's actually an important part of the story. Are there any other questions? Okay, good. So now we have these states. So let me ignore these for now. And they do play a role, but I'm not going to tell you about them. We've got 4 states here, and 2 of them correspond to a string stretched between them. So now I ask my Berry's phase question. Let me put myself in one of these states, and I take my D0 brane, and by hand I start to move it around. It doesn't even have to be by hand, I could just give it a flick and watch it move itself. But I'm going to move it around like this, around the D4s. The string remains attached all the time. I come back to where I started from. The Berry's phase question I want to ask is, if I start in one of these 2 states, by the adiabatic theorem I know I still stay in these excited states, but what's the rotation that the state's undergone within these 2 states? So what I'm looking for is a Berry's connection which is U2 valued. Okay, U2 because I've got 2 excited states. So I'm not worried about the ground state. You can ask the question of Berry's phase for the ground state. It doesn't exist. It's completely trivial. So the first case you can actually ask Berry's phase to get a non-trivial answer is for these excited states with this string attached. Okay. So we did the calculation, and let me just tell you the answer. So let me write down the question first. So sit in an excited state. Sit in an excited state. That means with a real string attached between the D0s and the D3. Move the D0. there's a nice topological answer or a geometric answer, which is that you have R5 is your space of parameters, and you want a U1 connection over R5, which in this case has to be SO5 invariant, and such a connection doesn't exist. Or you could just do the calculation. It's easy to see there. So the answer is the following, and I'm not going to write down the connection. Again, you run into problems with singularities and such like, and I'm not even going to write down the field strength just because it's not very illuminating. But I'm going to tell you the properties of this connection because it has very nice properties. So the answer is that it's not actually in U2, it's actually in SU2. And I think the reason it's in SU2 and not U2 is the same reason I just gave. You can't actually have a non-trivial U1 connection over the space of parameters. And it's what's called a Yang monopole. Okay, so if you don't know what a Yang monopole is, don't worry, I didn't know what a Yang monopole was until about a month ago. A Yang monopole is to 5 dimensions what a Dirac monopole is to 3 dimensions. Okay. And it has the following properties. So it's an SU2 valued object, not a U1 valued object. And here's my space of parameters. Okay, so this is R5, which is the space of parameters, which is the space of positions of the D0 brane, and there's a special point in the middle, which is where the D4s live. Okay. And the Yang monopole has the following properties. So as I said, it's an SU2 gauge connection over this space, and the property is that for any force sphere that I choose to draw centered at the origin, so this is some S4, this Yang monopole has the property, people see if I write down here? Has the connection that the trace of F wedge F integrated over this force sphere is 8 pi squared. Okay. Now this should look familiar from the last lecture. You know, this is telling you that you've got an instanton, but in the last lecture we were thinking about instantons in R4 with particular sizes. Here it's an instanton over a force sphere in R5. And essentially what has to happen for this whole thing to work is that as the force sphere grows, the size of the instanton is growing with it. So that's kind of the basic picture. This Yang monopole is singular at the origin, which, just as in the example I gave before, reflects the fact that there's new states becoming massless as the D0 brane hits the D4, and all these strings are becoming massless. Okay. So, yeah, let me just try and make the link to what I said before a little cleaner. In the original example I gave, we had a 3-dimensional parameter space, and over the Dirac monopole has the property that over every 2 sphere, if you integrate the magnetic field, you get the answer 1, essentially. It doesn't matter how big the 2 sphere is, the magnetic field is dropping off as 1 over r squared, the 2 sphere is growing as 1 over r squared, you always get the answer 1. This has exactly the same property, but what you integrate is F wedge F. It's the second Chern number, not the first Chern number. So, as the force sphere grows, the gauge potential drops off in exactly the same way, the right way, to cancel the r to the 4 growth of the side volume of the sphere. Okay, so this is quite nice, actually, the fact we found a Yang monopole. We were very pleased with this, because this is something that isn't new. People have used this Yang monopole for Berry's connections before. The first people to notice this were mathematicians. This guy, Barry Simons, who's somewhere in California, I'm not sure, and some of his collaborators. They pointed out that given that the Dirac monopole is the canonical example of Berry's phase, the next canonical example should be exactly this Yang monopole. It's to do with Hopf fibers. You know, the Dirac monopole is a U1, which is a circle, fibered over a 2-sphere to give a 3-sphere. That's the first Hopf map. The Yang monopole is an SU2, which is a 3-sphere, fibered over a 4-sphere to give a 2nd sphere. That's the second Hopf map. So it's really that the next natural Berry's connection in this sequence from the Dirac monopole to the Yang monopole. Rather nicely, it's also appeared in several condensed matter systems. It appears in the SO5 theory of high temperature superconductivity. It appears in ultra cold atomic gases when spin 3 halves fermions condense. Both these systems have precisely this object as their Berry's phase. Okay, so that was kind of nice that we found this. Let me tell you a couple of caveats. There's actually a whole slew of caveats that we needed to figure out here. So the caveats are to do with what happens when there's many D4 braids. And when is this calculation valid? It turns out that there's something like a Toff coupling which comes in, and this calculation is valid only when ng squared is much less than x cubed. So that's one caveat. What time do I have to finish? Was it 5? Shit. Oh man. Okay. But I was forced to finish early. Let me take 1 or 2 more minutes of your time. Let me not tell you any of the caveats. Sorry, I completely missed time. And let me just tell you how you understand this in terms of ADS-CFT. Okay, so what do you do with ADS-CFT? What you do with ADS-CFT is you take the D4 braids and you let them back react onto the space so that you take the supergravity solution of the D4 braid, then you take the near horizon limit. So the supergravity solution is something like minus h to the half t squared plus h to the half x squared, where this h is 1 plus ng squared over x cubed, and of course the near horizon limit you just drop the 1. Okay. So the cute thing is that you can find this Yang monopole directly from a classical calculation in ADS-CFT without ever doing any quantum calculations. And the deal is the following. You put a D0 grain in this background. Now, when people talk about a D0 grain, they usually just sort of think of a single particle. But in fact, of course, it's a whole multiplex of particles, a scalar of fermions, blah, 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 blah. So what you do is you put the excited D0 grain, which is a spin half object, inside this background. You then ask what happens to that spin as you move in this gravitational metric. Now, it undergoes something like parallel transport. Here's the spin, you move it slowly, the spin changes, you bring it back to itself, and it's undergone this gravitational precession. Okay? It turns out that the gravitational precession that it undergoes in the metric, where you drop the 1 and you just look at the near horizon limit, is precisely the Yang monopole that we saw in the quantum calculation. Okay? Another way of saying it is that the spin connection for this metric is the Yang monopole. So what we've done here is the fact they agree, by the way, is due to a non-renormalization theorem. This Berry's phase is protected by supersymmetry in this case. But the key point is that now we've got a new way of computing exactly using ADS-CFT, something which in strongly coupled quantum mechanics is very difficult, and what's more is very important in many systems. So the idea is that we take now, and this is work in progress, further quantum mechanical systems which are D0 brane probes of other objects. We compute the Berry's phase by taking the near horizon limit, figuring out what the relevant metric is, and simply computing the spin connection of the metric, and that has to tell us the Berry's phase of this quantum mechanical system. So this is another example where we can really use ADS-CFT to get exact results about strongly coupled systems that we really wouldn't have a hope of doing in any other way. Okay, sorry I screwed up the time, but I'll let you go for Okay, questions at the barbecue if anybody has any.